my name is Matthew Deere, and I'm here to give you some basic instructions on how to find and utilize Skew-T plots for severe weather forecasting. Basically, a Skew-T plot is a representation of the vertical profile of the atmosphere at a specific geographic place, like a city, for example. One good example is that every National Weather Service station across the country launches a weather balloon at 12Z and 0Z every day. Those are Zulu times. That's for Central Time, like I'm in Norman, Oklahoma. It's -6 hours, so at 6 a.m. and 6 p.m. every day. They launch these weather balloons, and the weather balloons make what's called a sounding of the atmosphere, records the temperature, dew point, the winds, and it publishes them on the Storm Prediction Center website, which we're at right now, Storm Prediction Center. It publishes them in what's called a Skew-T format. Now, how to find the observed Skew-Ts on the Storm Prediction Center website? It's just spc.noaa.gov. You go to Forecasting Tools and Observed Sounding Analysis right here. Now, that'll take you to the archive. You have a week's worth of Skew-Ts you can choose from. And we're just going to choose the one from today, this evening. It tells you right here that this is an observed sounding. And in this video, I'll stick to OUN, which is the Norman. So you have a timestamp, the day or the place, and whether or not it's an observed or forecasted sounding. So the Skew-T generated is just one type of sounding. It's called an observed sounding. The other type is called a forecast sounding. So you can go to any model website, any page that displays numerical models. I choose the College of DuPage. I think they've got some great graphics. I click on their numerical models here. I'm going to choose the GFS. Really, any model is going to give you good Skew-T data. So let's go down and let's just choose some convective parameter here. See if we can get some CAPE going. We'll talk about CAPE a little bit later. So I'm going to click here, and it's going to take a second to load. They're actually switching to some new software that's developed here at OU. So they're trying to work out some kinks, but it still takes a little bit. All right. So then it's going to give you their forecasted sounding. It still gives you a timestamp here for Tuesday, March 1st. And this is called a forecasted sounding. Now, a word of warning about forecasted soundings. A lot of usefulness in a Skew-T is really seeing the small details of the temperature profile of the atmosphere. So if you're going to use a forecasted Skew-T, try not to go more than 72 hours out from the current time. That's when models tend to start losing their good resolution for Skew-T diagrams. Alright, so let's talk a little bit about how to actually read a Skew-T. Now, the first thing that you're going to want to notice is there's a lot of stuff going on here. This is from the SBC website. There's a lot of stuff going on here. What I want you to first focus on is this box right here. This here is the actual Skew-T. What you have here is you have the red line representing temperature, the green line representing dew point, and the dotted line representing the path that a developing thunderstorm would take temperature-wise. So the reason it's called a Skew-T is you see these dotted blue lines here that are at an angle to the bottom. Those are the constant temperature lines. So here at the surface we've got a temperature of 71 degrees or about 22 degrees Celsius. But say you go up to 500 millibars, you find where it's at, and then you trace the diagonal line down, and you find that the 500 millibar temperature is actually about -15. You don't want to go straight down. That would give you an incorrect reading. That's why it's called a Skew-T. The temperature lines are skewed. So you go down diagonally along this dashed blue line, the same angle. And it's the same thing for the dew point. Dew point goes up, and it gives you a good indication of how much moisture is available in the atmosphere. Coming back to the dotted dark red line here, this becomes really important in determining whether or not thunderstorms are going to actually form. We'll get into that a bit in a little bit, but at first I want to go over some more basics here. On the right hand side we have the winds, typical wind barbs, as you should know about from maybe an introductory meteorology class or just looking at some other model data. but it gives you a very complete representation of the wind as it changes with height. Here you have the hodograph. Hodographs can be very useful for severe weather forecasting, especially tornadoes, but I'm going to skip those for now. They're more advanced, and basically all you need to know about wind can be found on the bar side of the Skew-T. Down here we've got some severe parameters, but I'm going to talk about those in the next section. So to recap how to read a Skew-T, you've got the vertical temperature, you have the vertical moisture, and you have the parcel path, the path of temperature that a developing thunderstorm would take. Now, before we talk about, let's just go into it. Alright, so basic severe parameters. Now this sounding is still an observed sounding, but if you notice, it's taken at the same timestamp as, or the same day, pardon me, as the observed sound, or first sounding. It's just 5 hours later. So in the first sounding, you see how this dashed red line has to cut underneath. So think about what you know about buoyancy. If the developing thunderstorm becomes colder than its environment, cold air relative to the environment sinks. Warm air relative to the environment rises. So if it has to go through this part where it's going to be colder than the environment, a thunderstorm cannot form. This is what we call a cap, a capping inversion. You'll see these a lot on severe days in the southern plains, where the temperature above the surface is actually warmer than the temperature at the surface. This prevents storms from forming, and how to break the cap, or if the cap will break, is one of the very, very key elements in severe thunderstorm forecasting. Moving down, you'll see that as the day warmed on, the dashed red line no longer becomes colder on the left side than the solid red line. It's always warmer, and warm air rises. Now, the difference in temperature between the dashed red line, the parcel, the developing thunderstorm, and the environment, the area that's traced out between these two is called convective available potential energy, or CAPE for short. Remember when we talked about the severe parameters a little bit earlier? These values here are numerical values of CAPE. So the best one to look at, I think, is either most unstable or the surface CAPE. Those will give you the most accurate representation of what type of thunderstorms are available that day. You'll see here that the CAPE value is 4,946. That is absolutely incredible. I believe this is a day that many, many tornadoes occurred over Oklahoma. You only need CAPE values in the 1,000 to 2,000 range to initiate tornadic supercells. Another big thing to look for in developing very, very intense thunderstorms is winds turning clockwise with height. You see here we've got you have winds out of the south at the surface and winds almost out of the west at 500 millibars. That is just indicative that rotation is going to get developing very early and very quickly. Now, back to the cap thing. You see how the inversion here is still present, but the ground has warmed up to a point where the parcel doesn't have to become colder than its environment. We talked about that a little bit earlier. This is one mechanism for breaking the cap, like I said earlier. Breaking the cap is really just allowing the thunderstorm, or the parcel, the developing thunderstorm, to rise freely all the way to the top of its trajectory. Here's where it becomes colder than its environment again, and it'll sink back down. So another way you can break the cap is perhaps cooling off of the mid layers. If you have a deep area here, like we see here, where the dew point becomes relatively low compared to what it is in the lower layers, as a thunderstorm begins to rise, it'll evaporate. And when you evaporate liquid water, it actually cools the environment. So that's another thing you can look for, is a pronounced dry layer in the 700 to 850 range. That will also help break the cap. So in conclusion, we talked a little bit about how to read a Skew-T. I gave you some instructions on that, and then I gave you some basic severe parameters to look for. A lot of CAPE, a lot of area between the dashed red parcel line, developing thunderstorm line, and the temperature line. And every sounding is going to have all of these components. And we talked a little bit about the numerical values. Oh yeah, sin here. This is pretty much a measure of the cap, how strong the cap is. Here you see at the surface, and it's most unstable, it's 0, so you don't need to worry about it here. But up here at the beginning, you have negative 199. That is a big number that's going to inhibit. So you see the forecast surface is 0, so it's forecasted to break the cap. But in the morning, there was quite a bit of sin keeping the storms down. So if you see sin in the negative 50 to negative 200 range, it's going to be hard to develop thunderstorms at the current time. But if you can forecast it, that's when you can see things starting to get interesting. So in general, Skew-Ts can be very, very simple and very, very useful. In the future, I hope that you're able to use these a little bit better than maybe you have been in the past, or I hope you're able to find them and start using them in your amateur weather forecasting or anything else that you might be trying to do with weather. They're also really useful for flying in the winter with freezing levels, but that's a whole nother story. So for the time being, I hope you enjoyed this presentation, and if you have any questions, never hesitate to contact me. I would love to explain Skew-Ts more in depth to you. Hope you have a great day.